The Winnipeg.net User Group 2016 season is brought to you by Aptius, IQ Metrics, Imaginet, Vision Critical, and Microsoft.
My name is Adam Krieger. I'm a software developer and I've got about 10 years of professional experience. I'm a consultant and I work primarily in the .NET framework, but also in other languages like, obviously the JavaScript, all the web stack and things like that, primarily in business. So line of business apps and things like that. So this presentation is called Stealing Time with the .NET ThreadPool for two reasons. One is that you're shaving off time by using more than one of your cores at a time. So you're actually making use of resources that most people have there but they don't make use of. And the second is you're not writing a lot of boilerplate code to try and make use of your concurrency. So you're saving your personal time as well as your company's or whatever organization you're coding for. So spoilers, concurrency matters. It's not something that I think we can ignore as developers. I think we need to make use of it. But also another spoiler, just right off the bat, don't use concurrency as your first option. It's not simple. It's not low yield. It takes a lot of effort to get into and to do right. So even if you're going to use like the ThreadPool or something to easily make use of multiple threads and multiple cores, it's still difficult. So don't use it as your first option, but ultimately when you do want to use it, you want to clean all the garbage out first and then focus what you're doing. So we'll talk about why to use the ThreadPool. Why wouldn't we just leave everything single-threaded? And then we'll go into how to use the ThreadPool, which is the main part. It's got lots of code samples. That's really the bulk of the presentation. And so I think at this point, let's break for pizza.
Sure.
So I said concurrency matters, and here's why. So why did we come up with multi-cores in the first place?
Sorry, can you make it full screen?
I could, yeah, but I'm going to be switching back and forth. So is it gonna do what I wanted it to? See, that's, yeah. All right. So why did we come up with multi-core processors in the first place? Well, the size of the transistors has been going down so much that they can't get any closer to each other without pumping far more power through them. So you can see over time, right around 2003 through 2004, that instead of going straight up, it kind of levels off, and that's because the transistors have hit 0.9 nanometers. And so that's the actual width of the molecule of silicate. So at that point, you can't get any smaller without splitting molecules, which just doesn't work, turns out. So because of this, they've decided to just put more cores on the same CPU. But scale demand hasn't fallen at all. Scale demand is actually rising because of the exposure of the Internet of Things, automobiles, wearables, all these kind of things. The fact that everybody is now socially integrated and they have multiple subscription services that are all tying into things has taken the internet from something that you sit down at and make use of to something that you're constantly using and you expect to be immediate, and that requires a lot of scale, and it eventually requires contention, which is what we'll get into later. And contention is why contention in deferred processing and divergence is where concurrency becomes scalable. And so multi-core processors are already here. We've already got quad cores on all our desktops. All my demo examples are on this wonderful 4-core processor that has 8 logical cores. So they're all going to run really fast, and my scale demos will look amazing. In production, it may not be the same way. You may only have 2 cores to make use of, or you may have a conversation with your infrastructure operations team to say, how many cores do we have access to? I'm going to write some concurrent applications because we really need the scale in this one place. Is that an option for us? Or are all our VMs single core and we should explore something like microservices to make use of scalable things? This presentation is more around taking that scale that you see from the microservice movement and putting that on a single machine, because that's possible. And I said in the start, don't use concurrency if you don't have to. If your problem is just that you're doing wasteful operations, and you can do things like improve your compute time, go down from get as close to linear compute as you can, and you can also step beyond that and do things like memoization, dynamic programming, caching, all sorts of things to like try and take work that you've already done and reuse it and make better use of that work. That's great. These are all things that work well in single-threaded environments. They don't necessarily need multi-threading or concurrency or parallelism to make use of. Although we'll get into why we're already in a concurrent environment. And you can also streamline your I/O to make sure that you're not pulling things when you don't have to, and when you are pulling things, you're only really pulling the data that you need to. It's a common place to rewrite an I/O call so that you're actually just sipping data off the top rather than taking all of the entities, trucking them over into your memory space and making use of them there. So that's another strategy that you can make use of to just not use concurrency in the first place, or not use the advanced multi-threading in the first place. So because of that, increasing complexity kind of puts you on the hook. Now, once you go into a multi-threaded environment, you now have to deal with race conditions, non-determinism. You have to benchmark and make sure that the extra complexity of not being single-threaded is actually getting you things. It needs to get you a speed boost. There's ultimately, I kind of philosophically thought back and forth on it. I really couldn't come up with a good idea of why you wouldn't do just single thread if it wasn't for scale, if it wasn't for trying to do things, trying to do more things through the same bandwidth. So what do we do when we're trying to make use of multi-threading? Well, the same thing that we do when we're trying to make use of other systems that are reusable and other systems that we've traditionally had to deal with, like boilerplate code or very repetitive actions. We take collections and we build wrappers around them, and then we take memory management, we build a wrapper around that. We use garbage collection, we take network and file I/O, and we dumb that down so that we're really just using a simple interface. And so now that with .NET Framework 4.5, where these kind of new async await patterns were introduced with, they're getting that way with thread management as well. So the ThreadPool, let's see, I'll get to that in a second. Let's see if I can show off a quick demo of what thread management was prior to 4.5. And this is a really, really simple operation, but you can see you're getting a new thread. You're just telling it to do something. That's all this lambda is. And you have to manually start this thread. And the reason I'm sleeping here is because, I'll get into that, but ThreadSleep basically gives up the rest of your CPU allotment and gives it back to the CPU so that it can give it to someone else. So that helps this demo just a little bit. So it says, fine, give up the rest of this thread's CPU time, come back to me later. And then it's just going to write some more console stuff. And then you have to do complex things like this. This thread is down here, running, sleeping, doing whatever it needs to. but you have to check whether it's alive in order to determine, what you can get out of it or what's happened. And you commonly have to take the output of those threads and store them someplace where you can get at them and manage all your non-determinism and race conditions manually. So as we go through these code examples, we'll get into why the extra tools that have been added in this update, which is actually quite old now, really help you out with these kind of things. So as far as the thread pool goes, you take these collection of threads, which is where you can see what I was doing in that demo was just instantiating a thread. It still uses those threads underneath, but it wraps them in a thread pool. So similarly to the kind of abstractions of complexity that happen when you pool database connections or other things like that, any kinds of resources, access to resources, you get a more flexible kind of thing. It's expensive to generate threads in the .NET framework as compared with other frameworks. I think each thread still takes up about a meg of memory, something roughly like that. So as much as you can reduce that, you're better off. There's other frameworks where threads are actually instantiated for like 8K. So it's far easier to work with them, and you can scale upwards of 1 million connections on a machine using those frameworks. So this is a rough diagram of kind of what it looks like. I modeled my machine, so I've got one CPU, but I've got 4 cores on that CPU. And then the OS is going to manage how threads get assigned to those cores to actually process the work. You can think of threads in this case as, or the work you put on threads as kind of like a nail having to be hammered into a board. Some of the nails are longer, but what the OS is doing is it's giving the boards to the CPU, to the core for short amounts of time. That core is going to process that, is going to try and hammer that nail in as much as it can until the OS says, okay, you've had that long enough, stop it, I'm taking control again, and I'm going to give you something else to work on. So this actually happens many, many times per second, where it's taking different threads and assigning them to the core and shunting them off. So you rarely ever see a thread sitting on the CPU for anything longer than you can snap your fingers. But it gets rescheduled right after that. So over here in other processes, they all have threads. The OS touches threads. You can see that if you look up the task manager performance thing, you can see I've got about 1,500 threads running around on my machine. I don't have 1,500 CPUs, so the OS has to juggle them around and figure out which ones of those are going to get processing time at any one point. In .NET processes, you can have several threads per process as well, and you can also, from your .NET code, manually instantiate them like we have, or you can make use of the thread pool, which has its own manager to take tasks that we create through advanced techniques and manage them amongst the threads that are being managed by the .NET process, and then those in turn get managed onto the CPU. So you're taking additional abstraction and kind of making use of a staged management buffer kind of pipeline kind of thing. So that's a lot of stuff that we don't have to care about on a regular time. The default time that a task or that a thread gets on the CPU is 15.65 milliseconds, which is about that, maybe even a little shorter. So you can kind of imagine that you really don't have to worry about things blocking other things unless you start messing around with thread priority, because the OS is going to handle shunting tasks back and forth, and nor do you want to manage things at that level of complexity. You kind of want to wrap things in a bucket and put a facade over it. So concurrency parallelism, a lot of people use them interchangeably, and I sometimes mess up, and I think I've done that once or twice already today, because it's really easy to get them mixed. So concurrency is when things don't necessarily have to start or complete at the same time. It's a non-deterministic thing. So this green task here may finish earlier or later than the purple task. So those are concurrent things. Whereas if we look at this single-threaded application, you cannot start this until or you cannot start this until that finishes. You can't start this until that finishes. So we're not talking about concurrency. Of course, we're still concurrent because we're running on an OS, and the OS is managing which thread gets CPU time, and that's non-deterministic. But within your program, in the context of your program, you are not concurrent. However, parallelism is when only for the points of time when you're doing things at the same time. So you're still concurrent over here because this may not have finished by that time, but if you look at how this is laid out, you're only parallel when things over time are running simultaneously. So that's a somewhat easy easy mix-up to make, and it's kind of important to get yourself in the right frame of mind when you're looking at these things. And so non-determinism, basically when the sequence of events may differ, and that may or may not actually have effects on the results, which is kind of where you get race conditions and most of your concurrency bugs from. So I went through this guy. This is basically the inventory marketing APIs are on different servers. They're across the internet. And most code that we write today, even if we call something out on the internet, we have to wait until that call gets all the way back to us before we do anything else, and we move on with the rest of our code. Even though this block in the middle may not make use of this for 100% of the time, it may do something else. We still have to wait for the whole time. Whereas if we start to make use of concurrency and multi-threading, then what we can do is make use of the extra time that we have on other machines and do other things while we're waiting for the other machines to respond to us. So you can also kind of think of the inventory marketing API as being potentially operations on the same machine if you're working in a multi-core environment. But even if you're not multi-core, you can still make use of the thread pool to do things like this, because these guys are running in tasks which can get mapped to threads. So having them run on separate processors and being maintained in the general thread pool, not on separate processors. Even if they're being maintained in the general thread pool, you can still have them holding on and waiting for the connection to come back from the other server while you're running your main thing. These guys usually just won't take up any CPU time, or they'll take up very little, 15.625 milliseconds of it. So into concurrent building blocks. So what do we need to know when we're building patterns to make use of non-deterministic multi-threaded or potentially multi-threaded operations? We need divergence, so we need to understand how to split off and tell the program that it's okay to do things more than one at a time, and which of those things are happening simultaneously or can happen simultaneously. We need convergence, because now that we've done things separately, we need to put them back together so that we can do something useful with them. And we have to deal with contention, because often when we split off and do different pieces of work, those different pieces of work need to communicate with each other, and they often have to contend for resources, such as I/O, such as even places in memory, which we'll get into. So for divergence, this is kind of the start of the meat and potatoes, basically the async and await. The pattern, these syntax building blocks that are kind of the poster boy for the 451 concurrency wrap. The biggest misconception that I found floating around on the internet was thinking that once you called an async method, what you were doing is calling or creating another task, and that task was like eligible to be scheduled on the thread pool, and that's not exactly how it works. Async is a modifier that you put on a method so that you're signifying to the compiler and to anybody else reading the code, coincidentally, that method does something asynchronously. The compiler will warn if that method doesn't await on something. We'll get into await in a second. And that method always returns a task. So when you're using await, this is where your await is a prefix on whatever you're going to call into that says return control separately back to the calling thread while this continues on. And that's where the divergence happens. It's at the await, not at the call into the async method, and that's probably the biggest misconception that I found while researching this. It's the symbol of divergence, and the rest of the function after the await call will have to resolve before the actual result of that async method comes back. So I know that's a lot all at once, so let's go straight into a code demo. So you can see that this method is marked async, and it returns a task. This is probably the simplest thing we could do with async. Return to basic. Tasks are generic, so they wrap classes, and you can put whatever type you want into them. Get value async is also another async method which creates the task by calling task.run and wraps the anonymous method and then says, let's return this task so that we can run it. The task is really just going to sleep for 500 and say and indicate whether it has or hasn't afterwards. So the reason I mentioned about the rest of the async method continues to run after, so it's not like the await is the actual point of return. The actual point of return is still the end of the method. The code in there still happens. It's just the await is when you return to the calling method. So anything in between await and the end of the method is kind of where you're getting your concurrency. That's the point of code where you have to worry about things hitting things like race conditions if you're using contention, or if you're using more pure functions and methods and they don't actually touch each other, then you're all golden. You're just getting bonus at that point. So what that means is, even though I'm awaiting here, at this point I'm returning control back to do work async, and it's going to be able to run this console write line right away, and it's going to get one line down, and then it's going to await the return of the task. So it's going to wait for this task to finish at that point. Down in here, it's going to finish the ThreadSleep, and then it's going to continue the rest of it, update the value that it returned just to show that it actually does run the rest of the method, and it's not just returning here, because another misconception I've seen, not as big as the other one, is that await is actually the thing that's being returned back to the caller, but it does run the rest of the method and returns the result. And then we say we've got the result after we're completely done, and we exit. And that is too small for you to see. Okay, so let's run it, and I'll see if I can zoom in here.
I think you can increase the font size.
I should be able to.
Change the properties a little bit.
Properties. Not good enough. Yeah.
There we go.
So one thing that's interesting about this is this time I have the task ran before sleep for 500. Let's get those both on the screen at the same time. But we're already in a place where this is non-deterministic, because sometimes when I run this, sleep for 500 happens before you see the I have the task. So we've already diverged at that point, and those two guys are running off separately. And because I've got lots of cores and plenty of things to work on, it's going to be really common for those things to actually hit before each other. So you're already in a race condition. Whereas if you were doing something that mattered, it doesn't really matter to me, it's printouts on a console. But if you were doing something that mattered, you would have to be really careful and watch your back. And you can see that ref value is updated, so it's getting what happened after the task has finished running, not what is awaited and being passed back to the calling method. So these guys are really easy to make use of. The only thing that's a little tricky that I kind of wanted to make use of is that whenever you're calling task.run, it just takes actions, so you don't get to pass parameters into it. But what you can do is make use of closures. So you can say var value.
Did you just say closure?
Yes. I can declare a value outside of that anonymous function, and I can console .writeLine it in here. So I have access to that, and that's kind of how you can get around passing values into functions. If you're going to go anywhere more complex than just passing a simple value into a function, you probably want to make use of a concurrent data structure or some sort of shared place that you're going to look for and contend with inputs. And that's like 4 examples down the line, but.
Hey, Adam?
Yep.
Can you clarify when you say that if you use pure functions? what
Yeah,
does that mean?
so pure functions are anything that don't have side effects. So if you modify something in a static namespace, that's a side effect. If you write something to the database, it's a side effect. Like, the list goes on. Things that aren't side effects are actually a far shorter list. That's modifying things in your own memory namespace that nobody else has access to, or heck, even if it's a database that is only set up for that one thread. But that's a pretty rare instance. So it's anything that doesn't affect anything outside of the domain of control of the thread that you're running. And that gets important when you're talking about parallelism as well. If you've got a collection of 100 objects, you don't want them running over and causing contention and problems with each other. You want to make sure that those 100 tasks either are very careful about when they touch things that each other are going to use, or that they never touch things that each other use. So one of the two. So to reiterate on that point, maybe hitting it too hard. Don't go do that while I do this. Is async and await. But here, let's work on this in the call stack. And are you good for a while is when you're saying await. You're good for a while? Great. I'll go do what I was doing before. You keep doing this. I'll ask you how you word. I'll go check on you later with either another await statement or using result or wait. So sometimes when you're on at that outer level of concurrency, which is now when I can show you the basic open here, is I've set up a little bit of a menu around these choices. But at the root, what I'm doing inside my stopwatch calls is I'm calling wait. And this makes sure that everything, zoom. This makes sure that everything I'm doing in between my start and stop has happened. This will collapse and wait for everything under there to work. There won't be another, if I've done it correctly, there won't be another thread floating off in the background continuing to do work somewhere else. There's a minor point in there about how ThreadSleep is ThreadSleep gives up your remaining share of the CPU time. So sometimes I've seen it used in benchmarking, and it's not applicable. You really have to use things like spin weight or like just a for loop that just has a certain number of cycles, because it actually has to do work on the CPU for it to count. So back here, hopefully this diagram, if you weren't familiar with those concepts, this diagram is a little bit more familiar now, whereas you can see that when we call into get async and returning an item array, we are calling an async method, but it's not until the blue arrow comes back where we're awaiting on the result of that. And that's actually a return. So this could even be the last statement of that method. And it's not until the whole thing, which is synchronized with this web call, finishes, that the task actually is able to be resolved and comes back. But since we've awaited, we can go back up to our main thread and then make another call out to another asynchronous method, which also calls out to coincidentally a different web service, and that thread maintains for the life of that web call. And then when they both come back, we can get the result of either of them, or the result of each of them, and then continue on and merge them and converge back on where we were before. So you can see that red block that I've highlighted there is, in this case, we called result on items before it was ready. So it sat there and it blocked the thread, which if you're in a desktop or a user situation, you wouldn't want to do. But as soon as you're in like a web situation and this is on the server, it's not that big of a deal because nobody's locking up. Or as soon as you've wrapped it, like you were saying, a couple levels deep, it's not that big of a deal. You may actually need to wait to go on. And then you can see that the purple result, the deals.result, is actually getting its result after the task is finished. So the task is sitting there waiting to be called on, and its results are sitting there ready to go. So there's also another interesting control flow called continue with, where you can take the result of one task and then chain it to another one. This demo is pretty quick. Oh, it even kept my font size. How about that? This one's pretty quick. It's still pretty much taking one task and chaining it into another is done by, we had this anonymous function, we go task.run, and we wrap the anonymous function, and then we can chain continue with off of that, and you'll get the previous value, which is the result of that task, the unwrapped contents of that task. You still have to call the result on it inside here, and then you can do whatever you want with it. And what you end up returning here is another task of whatever object you're working with. So to hammer that point home, I did another continue with and put plus something else, but also this. And you can see that it's going to run those, and this is deterministic. They will always run in that scenario. It's not like you have these continue withs and it'll occasionally run this one first. These are chained and they're ordered. So that's an important thing, especially when you're working with like invoice transactions where you commonly need to do 4 or 5 things in a defined sequence, and you need them to happen in order. But hey, it's sure handy if they were multi-threaded. Great. So moving on to convergence. So this is how we're taking all the things and we're kind of pulling them back together. I've been converging this whole time because it's really hard to show anything useful without doing so. But there's a couple different things we can do to converge. So let's say you don't want to converge when the task is finished. You want to cut it off. So this is sometimes when if we fire up a subscriber or some sort of deferred process that kind of like lives on its own, and we want to say, come back, I'm done. You can use a cancellation token to kind of reach into that task and tell it that you don't want it to run anymore. But the task, it's important to denote that the task is actually in control of the cancellation. So you can give a task a reference to a cancellation token, and that task doesn't have to listen to it. It can, if it never checks the status of the token, it's not like it's part of the task where it closes out. This is one of those things where you actually have to handle the cancellation yourself. So in that case, you have to create a cancellation token source, which allows you to have things like static tokens, or you can store the token source somewhere else, and you grab the token off of it. And this is a bit awkward as far as syntax goes. You have to pass the cancellation token into the task so that it has a reference to it, but then you also put a cancellation token on the task run. And that's just to indicate that it supports cancellation. But if you sit there and cancel the token without passing it through and without that task checking it, it doesn't cancel anything. It'll continue running forever. So this guy will sleep for 3,000 milliseconds, and then it'll cancel the token, and then it'll wait for the callback. And down here in the actual cancelable task, I've just got it running for 10 seconds, so it should be cut short at 3 seconds. And for each second, it says, is cancellation requested? And if it is, then yeah, sure, I'll comply and I'll cancel. It's up to you. You can choose to do a cleanup task, something that like closes all your connections and deallocates some of your resources or whatever you need to do to clean up, and then return. And this kind of echoes outwards. And if you're running a microservice or something that can be canceled from a remote source, or even if the operating system signifies that you're closing it via just closing the console window or something like that, then you can have that on dispose, call the cancellation token of your inner process, and that cancellation token will keep the thread alive and thus also keep the processor alive until you go through your processors, go through whatever you need to and let it return. So at that point here, now we've let it return. So if I run this guy, the cancel example, you can see it's going to run for 3 seconds, not the full 10, and it's only because I've said I waited for 3 seconds. It's only because I've checked for this every second that I'm able to cancel and go back to the call. WhenAll is another interesting one for convergence. So this creates a task which wraps a task array. So if you're waiting for multiple things to complete, and you don't care, this is another one of those things where it's like a shortcut. You don't want to check each task and say, is this task completed? Is this task completed? And sit there spinning and waiting for those things to happen. Why don't we take whatever tasks you want to finish, wrap them in another task, and when that task finishes, now you just have to await one task on one line of code, and what you'll get is you can run 3 or n things in parallel, it comes down, you wrap it in one task, and when that one task completes, now you can go back and continue. So if you're doing like 3 data pulls, you need all those data pulls in order to construct an invoice. Wrap those in task arrays, and wrap those into a task array, and then use WhenAll on that task array, and it'll come back to the await when all of that finishes up. So in WhenAll, you can see that I've even, pardon me, in this one operation, I've gone non-parallel, and I've got a count of 1 to 10, and I'm going to wait. How long was I waiting? So this wait is actually doing a spin wait. So now I've gone into the section where I'm actually using CPU time, and I'm no longer, just sleeping at this point, and I want to record the values from all these. So in here, I'm making use of the link library to kind of simplify how this looks. And what it's actually going to do in the background is it's going to go through 1, 2, 3, all the way to 10. So when I run in parallel, I've actually piped it via continue with, which we've already seen, into a print and continue method, so that you'll see the output in the console window in the order that the task actually completes. But I guess we'll see that it comes back, and when you call WhenAll, it's going to come back in the same order. So it doesn't return in the order that the task completes. It returns in the order that you gave it. So that your array will still be in sequence, which is really important if you want to do anything that has any sort of like you probably spent a lot of compute time to sort things in the first place. You wouldn't want to resort them after you went through an asynchronous operation. So if we call WhenAll, you can see that it's going to wait for a little while, and non-parallel is going to finish in about 9 seconds. Oh, this is even running faster. I don't know what I'm doing differently. But you can see that the parallel operations of counting 1 to 10 and running, what is this, 20 million? 200 million? 200 million cycles through my processor in a row takes about a second per run. And you can see that the tasks, they all take the same amount of time, but because of the way they're being scheduled on the CPU, it's inherently easy for them to be non-deterministic and for them to finish before one another. So even though when you schedule them on the CPU, it's not necessarily being done in a guaranteed sequence, if that makes any sense. The natural order of the thread manager can cause one of them to finish before another, and in this way we've seen that the lower numbers like 1, 2, 4 tend to be at the beginning. That doesn't mean that they're always going to be in order, and in this case it's really difficult for them to be in order. But down at the bottom you can see that when we do have the results, they're back in the order that we started with, which is really important. And this is also the really big kind of aha moment, where if you open up the task manager and take a look at this, I'll run this demo again. Where'd my task manager go? There we go. So if I go WhenAll and we take a look at the CPU, you can see that it sort of started out a little low around here. It's processing around here. And as soon as it hits the parallel operations, it spikes. So we're not even while we were doing the non-parallel operations, we weren't even making use of the power that we had on this system. But once we told the .NET framework, it's okay to do these things in parallel, it said, great, I'm just going to use everything I have. Didn't even, didn't peak out at 75 or anything like that. It just said, I'm just going to take the entire system. So it's really important at this point, and I've seen this in production a few times, is when you go parallel, you have to make sure that now that you're making use of all the resources, you don't impact the fellow services on that machine. Now you're in a space where you're in a space where you're contending for resources, because it becomes survival of the fittest at that point. So that's really a good argument for having these small VMs in the cloud running one service, if you can stand it, and then just try and make that service always make use of resources that it has, that it doesn't have to contend with other services on that same VM. Right.
Will the operating system not help control that a little bit? Like, if you're spinning up a lot of processes like that, will things just start misbehaving? Or
If you're on the thread pool, it just seems to take all it can get. The operating system will do its best to make sure that you using the computer is still responsive. It prioritizes the UI and the kind of critical functions of the computer that from a user's perspective. But when it's sitting on a server and it knows that those aren't relevant generally, you can set it up so that these processors, if it's maintaining a UI, it will still try and keep that UI present to the user. If you're managing the priority yourself and going outside of the thread pool and kind of addressing the priority yourself, then it'll respond in kind, and it'll basically do what you told it to. So that was the big payoff. That was the stealing time thing. That was really just taking, let's say we have a massive amount of work. Well, let's just call it with a slightly different syntax, and now we've compressed it into a much shorter window. So there's a lot of complexity that can go along with that. There's a lot of contention and some interesting kind of server load stuff, but hey, wrap it in the thread pool, use a system that's already there that we don't have to write the boilerplate for, and we'll get some big payoffs. And moving on, I also saw as parallel, which extends IEnumerables. Yep.
Sorry, maybe I'll get to this later. But a question I have is, when you're designing something, when you're starting to write code for an application with your team or whatever, do you start thinking about when's the point you start thinking about running things concurrently or in parallel? You start writing your code, because clearly you got to write your code a little bit differently. You got to make some choices. Is there a point where everyone just kind of goes like, you know what, we should have written this way, and now we're gonna change, like refactor? Like that's always the part I've heard, that sort of like, we should have done it this way. Mm-hmm. But I've never heard anyone go back and do it unless it's been business critical or sort of like it's really huge. So my question is, when do you start thinking about going in parallel? Like when, like in your experience?
I would say it's something that you have to design from the ground up. So if you start off with something that is laid out, maybe it's been there for 2 months or 3 years or whenever. If you try and slap and like butter concurrency over top of it, you're going to wind up with problems. Okay. You really have to restructure, at least pick where you're going to start from and where you're going to stop from, and redesign what's in there and make sure that it follows along with concurrency, so that get it as close to pure non-contention as possible, and where it does contend with resources, do that safely. And so make sure that anytime that it has to diverge intentionally, converge intentionally, like make sure that your code interlocks at the right places. If you just kind of say, let's just throw concurrency into an application without thinking about race conditions, guaranteed there's going to be some static something or other that when you try and access it here, and then here, it's going to break. Like we could see, do I have a great example of that one? Yes, I do. It's coming up.
Okay, cool.
So as parallel, I think Link is one of the best things that they've added to the .NET framework in quite a while. It allows you to take any collection, kind of wrap it into an enumerable, and then use functions to kind of go in and out and sort of stream things through. Is there anybody not familiar with Link? Cool. So there's a really simple way. I just showed you WhenAll, but now all this sort of this wrapping of tasks and whichever, this is going to go away right away when I take a look at the parallel sample. Oh. All of this can get squished down into a single line just by chaining the enumerable through as parallel. And it's going to do the same thing. It's still going to be able to run non-deterministically, but then compile back out to the same order. So I'll save you the benchmarking, but it does exactly the same thing.
Is it from enumerable or iQueryable?
Enumerable. I'm assuming you could chain it off of iQueryable as well because it inherits from, but it's all the way back up to enumerable. So same great code, but or same great performance optimization with less code. And now that we've kind of focused on how to get the results of tasks back into one central place, now let's talk about contention. And this is I guess it's a bit of work on how to set up the building blocks. But now once we get into like how do we care about thread safety? How do we care about this is kind of a topic I've been alluding to for the bulk of the presentation is what is thread safety and how do we ensure the thread safety? Thread safety is about making sure that when a process, I say process, but what I really mean is when a sequence of events thinks that it owns something, it owns it. It's not going to go through sequence step 1, sequence step 2, and then go to sequence step 3 and figure out that something else has changed what it's looking at underneath its nose. So thread safety is about making sure that for at least intentionally brief periods of time, you've taken shared resources and unshared them and kind of owned them and made them yours for a while. So that's one of the more basic ways of dealing with it. So I have a non-thread safe demo, which crashes at varying points in time. So it'll either be flashy or it'll either be like, oh, that didn't really do anything at all, or we'll actually kind of see what's going on. So I've implemented a queue. My unsafe queue makes use of a regular old queue data structure. And we've got one publisher, which grabs the next sequence and in-queues something onto the queue. And then we've got two consumer threads. So there's the exact same function that's consuming, and that consumer thread is saying, well, we're not canceled. We're going to make sure that thread count is greater than 0, and then immediately we're going to dequeue it. So these two things are like, they'll compile down to 2 lines of syntax away from each other. And hopefully we can see how easy it is to write things that aren't thread safe.
Should that be the goal?
Sorry?
Should that be the goal?
To write things that aren't thread safe?
Yeah.
Yeah, I think so. At least once. I mean, that was my goal here. So you could see, I actually had to sit back and think, how can I break a queue? So I actually got all the way to 8. A lot of the time it only gets to 4 or 5 before you try to, you say, hey queue, do you have any items in you? The queue says, yep. Then I'd like one. Don't have any. So that's basically what happened here, and you can see that it's really 2 lines away. It just checked to make sure that the queue had an item in it, and then when it says, give me an item then, it doesn't have one. So it's really, really easy to write unsafe operations.
It's interesting that it consumes 6 twice.
Yeah, that too, eh? And that's because the queue itself is unsafe. So not only is it unsafe because of the piece where it says, do you have any items? Great, give me one. Oh, I don't have any anymore? It's two different processes saying, give me an item. Okay. And it gives it to both of them. So what do we do there? Concurrent collections are built into this whole, the same system threading library that holds the thread pool in it. Oh, sorry, no, they're under system collections, concurrent collections. Sorry, let me get the namespace right. System collections concurrent is where they are. So those concurrent dictionary, queue, and stack, which are pretty darn self-explanatory, and then bag, which is kind of weird because nothing else is called bag, but it allows duplicates and it's unordered. I don't know totally of a use case for that, but I'm sure it comes up. I think I would probably more use dictionary and queue and stack, but. So how does the availability of a concurrent collection change our code? Really, we've instantiated the concurrent queue up here, and when we're in-queuing it, it's the exact same method signature. We're just putting it onto the queue. And when we're de-queuing it, now we're doing this in one line, and we're saying, hey, concurrent queue, can I de-queue? And if I can de-queue, I've got the object. That's the one line of code that it executes. I don't have to check on one and get it on the other. So that takes out the contention that we noticed originally, and it also takes out the contention that you noticed where we're gonna make sure that we don't have this, because the concurrent queue under the hood is gonna say, if someone's asking me for a value, I'm going to say, hold on, wait, give this guy the value. Okay, now what do you want? And it's going to turn to the other one. So it does mean that it's blocking that other thread, but that's where we make things thread safe. We have to have enough to do in a multi-threaded parallel concurrent environment that we separate off and do things separately, that it justifies that, because we are going to have to contend with centralized resources. And in order to contend with centralized resources, we have to create situations where we block the other pathways from accessing those centralized resources. So you have to, just because you're setting up ways to do things simultaneously, you now also have to set up ways to not do things simultaneously.
But only done by first identifying, right?
Yeah, identify where things are going to contend with. Right, and if you have to do 10 things, but only the last 3 care about the sequence of events, that's where you should lock. That's where you should hold it down and say no one else can touch it while I'm doing these 3 or 4 things. And that can be really important when you're dealing with unique identifiers or like finite resources, like when you're pulling things out of inventory and saving transactions online. You wouldn't want to send the same piece of inventory to 2 different people, because that's digitally possible but physically impossible. And so when we run this guy, we'll go with the concurrent queue example. And you can see that it's going to, I've also amped up the frequency to try and hit problems. And you can see that it's going to consume 2 in a row sometimes, and it's going to publish 2 in a row sometimes. But I've never found this to be out of sequence. And if I did, I would flag a bug with Microsoft. Because that's what they're supposed to be there for.
You've consumed before you've published, I guess, as far as the UI is concerned.
Yeah, as far as where the console cares.
Yeah.
So I could wrap that in a mutex or a lock to make sure that I wasn't able to publish to the UI before one or other, but the individual consumptions and publishings are going to be in sequence with each other, even if they aren't in sequence together.
So near the bottom it says consume 21, consume 20. So
Yeah, that's the race condition with it getting. It's actually this happens occasionally when the CPU thread it's finished publishing one message to the console and then cuts that off from having access to the CPU. And because these tasks are so small and run so quickly, it can go to the other one. The other one can launch. It accesses the CPU. It publishes the console message, and then the other one gets to come back onto the CPU. And that's how you get an out of order race condition with the console window. Which, when you're doing things that are just so fast like this, you get more visibility into the foibles of it. If things take like 5 or 6 seconds to run, it can be really hard to reproduce them in production. That's actually a great note. One of the easiest ways I've found to reproduce concurrency issues in production is to write stub interfaces around resources that we have to contend with. And you write these stub interfaces that really do nothing but return some sort of unique value back from them. And then you'll get the results very quickly, so you increase the chances of race conditions and possibly deadlocks and things like that.
So do you really need your if concurrent queue count greater than 0 check there? Is that just an artifact from before? Or is that still needed with the try queue?
You know, I refactored it. I'm not totally sure. I could just try and comment it out, but it's. I just left it in, to be honest. I wasn't sure whether this try DQ was going to throw some sort of empty queue exception, but that wouldn't make sense. It probably runs fine. Yep, that's a good point. Let's copy past a problem.
Okay.
Yeah. So concurrent queues, I ramped up the consumption on that. We didn't get any error. That we were able to write something that was thread safe with the exception of the console wait if we were considering that a problem. And the only difference was that we wrote a try DQ or a try pop thing, depending on what data structure we're using. And we used the out parameters, which if you're like me, you hate out parameters, but such as .NET. Huh?
We need an option on that.
We need an optional there. Yeah, that would be a perfect use of it. Some sort of monad, anyways. And so I briefly mentioned mutex there, short for
I have a
each.
question.
Yeah, quick
Oh,
question.
yeah. What's up?
So assuming the regular queue even had a try the queue, because it doesn't lock on that, we can still have a race condition, correct?
Yeah, so when you, and this gets into the other, that gets back to the other point where two threads made it to the DQ operation at the same time. They both entered that call stack, and then they were actually inside framework code for those collections. And I mean, you could write this on your own by writing by wrapping your own sort of queue around a list or whatever and debug into it like that. But you're actually inside framework code accessing the default collections, and somewhere in there's got to be something where you do something here, you do something there, and you would have had to get here on the other thread in order for this to be impossible. But because they both proceed simultaneously, they're able to do incorrect things out of order to each other. That third thing being where you update the shared resource. So using mutexes, you can do things like lock down, if you wanted to lock down like the console window that like we had in the previous ones. If you just blanket things with mutexes, you can defeat the whole purpose of multi-threading. So this kind of like gets back to it, like don't bother being concurrent if all you're going to do is lock everything behind locks and mutexes and protect it with things. You actually have to have some things that can proceed in isolation from each other. And this is, and if everything you're doing is a pure function, that means everything you're doing can be in isolation from each other, right? So, but that's not always the case. Usually you're accessing a database or some sort of whatever.
Locks and mutexes,
Mutices.
do they play fine together though?
I'm not sure, but I would probably not want to use them, or at the very least be very careful about debugging and making sure that they could play well.
Just they play nice together, like they're both guards, right?
Yeah.
They should be fine.
Yeah.
If you use it together, you mean?
Yeah, like open a lock and then open a mutex underneath.
No, I mean
Or
with
vice versa.
with the await.
Oh, do they play well with like the rest of the constructs of the async await kind of stuff?
Yeah.
As far as I know, I haven't encountered any problems with them yet. So a very basic mutex example is you take the previous kind of idea of a queue, and instead of having two consumers, you have two publishers. I'll take this. Yeah, I'll zoom in a second. I'm going to call the non-mutex code first. So this publish in queues. And so it's going to grab this concurrent sequence. This is like a metaphor for anything that you need to make sure only happens once. Or you need to kind of lock down on the input side of it. The other side where you could use, sorry?
That you need to make sure that it happens together.
Yeah, exactly. You need to make sure that this line and this line happen together. Even though we were able to take the DQ operation and pull it back into one line that the framework guarantees is thread safe from thence on down. Up here in our code, we often can't do that. So in order to create thread safe operations, we need to somehow make it so that these two lines are guaranteed to run in lockstep, or guaranteed to run one after the other, and no one else is able to kind of slide in between and modify a shared resource while we're doing that. So running this one, this is, I'm going to run the mutex example without the mutex, and you can see that, let's see if we find any bad publishes. Did we actually not get any this time? It's funny, I don't think it skipped any this time. 13, 14. I've seen worse than that.
That's probably just the console output again.
It might be, yeah. 6, 7, 8, 9. There you go. Published 5 twice. So we were actually able to get the value of the sequence twice with the same value before the increment hit, and then pass that on to the publish. So even even though we're using the plus plus operator, we're still able to get the same value from concurrent sequence twice. So now what I've done to make that thread safe is you make a mutex. You start it off false, meaning it's not owned by anyone. And you say, I own it if I try and wait one. Wait one's a bit of an awkward name for that function, but it basically just means you're trying to own the mutex for 50 milliseconds. You wait there blocking for 50 milliseconds, seeing if you can get ownership of the mutex. If you can, you come away with ownership. If you can't, then you have to check your owned Boolean to find out if you have it or not. So if we do have owned, then we're going to do this, and we're also going to do that in lockstep. I probably could release the mutex after that point. So this is all about factoring. You kind of want to be, you probably want to be more obtuse and initially lock down more than you need to, and then kind of scale it back, just to be more safe if you're thinking about where to organize things. So you can see it staggers it, and it also seems to run a little slower. So that's because it's running in lockstep. That's because it's owning the mutex. And when one thread goes to try and own the mutex, it has to wait until the other one releases it.
Question. So you waited for 15 milliseconds, you said. What's the normal wait time, and what happens if you don't get ownership? Do you just continue execution?
Yeah, like it'll come back with a false, and it'll say we waited for the whole time that you told us to, and we couldn't get ownership of the mutex, and then it's up to you as the programmer to deal with that scenario.
You could retry later.
Yeah, you could retry, or you could pass back and say we couldn't get access to the resource, please refresh, something like that.
Okay.
And as far as what the optimal time for waiting is, it depends on your system. I wouldn't prescribe any particular number.
There's a library called Poly that helps you with retry situation.
Oh yeah, like it algorithms it out. Yeah, cool.
I think it's Poly.
Or I guess it would be more heuristic at that point.
We don't have interlocked at all in that situation, for that specific situation?
The which, sorry?
Interlocked library?
Interlocked library. No, I haven't checked that out.
It's a thread safe system for incrementing and decrementing numbers.
Oh yeah. Okay. Yeah. Yeah.
That would take care of that one specific situation.
Yeah, it would have.
not
Yeah. Absolutely. I think if you got creative with a concurrent bag, you might be able to deal with it as well. Not sure, but something else to fiddle around with. So that kind of covers all of the basic building blocks and the basic kind of reaching into things. There's other things where you can take control of scheduling, and you can be a little bit more concerned with the priority of how your threads run, and a little bit more involved there. Then you're just getting more and more into like the danger zone at that point. Like if you can't solve the problem with the basic building blocks, it's got to be one heck of a problem. I'm pretty sure. So that's basically it. There's a few things which I don't really have the time to go over everything in detail, but exception handling is really tricky. If you call result on something, you collapse the asynchronous structure, and there's a possibility that you can get more than one exception out of that. So you have to recognize that what's always going to come back from that scenario is an aggregate exception, even if you only get one exception. And that's easy to see if we take a look at the exception handling example. Is faulted is a property on the task that you can check, and it's true in both of these cases, but in the first example, I've awaited the task, and in the second example, I've called dot wait or dot result on it, and it's actually collapsed it into an aggregate exception with an inner exception of an array of 1 with a not implemented exception in it. Just use not implemented for fun. So exception handling can be tricky. It's always best to handle exceptions as close to the place where the exception is flagged and not to overcatch when you're dealing with these kind of things, and then to try and make everything safe throughout. Try and avoid possibilities where things can be null. Try and avoid a possibility where things can have bad casting, or like you screw up something on reflection, like you expect something to be there and it's not, something like that. Try and isolate those things behind facades and then catch the exception on that deep layer so that you don't wrap all of your asynchronous code in one big try-catch. Because you're just going to get aggregate exceptions that are really hard for your code to deal with at that point. And as far as how other asynchronous layers of different frameworks work, the best one I've seen is the OTP section of Erlang, the Erlang, I guess, base library it's probably part of. Now that one has a full-on like supervisor mentality, and it actually encourages its individual tasks to fail, and then allows you to create, like, it's got prescription and boilerplate abstracted away for supervisors. So you can create a supervisor that says you keep track of this, and say you keep track of this task, and set up a strategy for what you want that supervisor to do if that task fails or takes too long or shuts down or whatever. And what you end up defining is process trees. And if a branch of the tree dies, you can tell a supervisor to rebuild it. So you can build all that in the .NET framework, but you have to be a little bit more deliberate with it, and you have to write some more boilerplate and debug a lot more, obviously, because you're kind of reinventing the wheel. I don't know of any libraries out there that'll do the same thing, but I'm sure there are some. Using the ThreadPool is similar to the way you would use garbage collection. You don't want anything to sit around for a medium length of time. You usually want your tasks to either be long running, and if they're really long running, you might even want to manage them yourself and not use the ThreadPool to deal with them. Or if they're short-lived, let's just use the ThreadPool. The ThreadPool's great at dealing with that kind of thing. You want your tasks to just roll through and run in a multi-threaded context that way. Similarly to how in the garbage collection, anything in generation 0 is like very small things that you're going to throw away right away, and then it gets promoted up to generation 2 with things that are like in a static context and are around for a very long time. So you kind of want to push away from the middle ground. It's just another thing to think of while programming, is if you didn't have enough. Like this is a general rule, I think, for any performance optimization, but especially with asynchronous programming, is you want to use a lot of tools for benchmarking. I showed you just the task manager there, but Visual Studio has a pretty sweet performance analyzer built into it. Performance and diagnostics. Oh, that ain't it. Yeah, that is it. So you can see here that you can monitor contentions in this case. Where's my CPU monitor? And you can create these nice graphs inside Visual Studio that monitor, and I've got another contention in there, but you can monitor like CPU load. You can do memory profiling in there, so you can see how long these things are sticking around. So make use of this guy, as well as even just making use of something as simple as the stopwatch, which I've been making use of many times throughout the example. So there's a very low-tech option and a very high-tech option for you. And know your production infrastructure. Get involved with your operations staff. Know how many systems you're running on. Know what the specs of those systems are. Whether you can boost those to multiple core or not. Those kind of things. I ran a demo on a blog post where I created a very basic web API thing that just ran a bunch of instructions, a bunch of dummy instructions on servers, and then I set it up on different levels of Azure Box. So if you set it up on, what's all this? Yeah, so this is basically all the code. It's very, very simple code, just running tasks and then waiting on them. You can use the await keyword inline and things like that. It's pretty fancy. And then you can see the results, which are, I didn't do too many trials on it, but I tried it a few times. It kind of came up with some, I tried it about 3 times for each of them and then just came up with the mean. And you can see that on a 4 processor shared Azure web app, this is like percentage of the synchronous. So when you're at this, like right up to a 10,000 or 100,000 cycles, there's no reason to use async because the overhead is outweighing what you're getting out of it. Your production code is actually going to be much faster if it's synchronous, if it's inline, if it's single threaded. Once you get past that, however, you get into this point, the sweet spot's at about 1 million, I think it was. Yeah, at about 1 million instructions pounding against that CPU. Then, and this is only 2 tasks, and that thing has 4 processors, so the other 2 processors are kind of wasted. So these 2 tasks going in on these CPUs at 1 million instructions, that's when it equates. That's when you deal with 100%. So it's no faster to use async than it is to not use async. But anything after that, you're in the gravy zone. That's when you're actually saving time by using more than one processor. And you can see that this is proven when I took that instance, the exact same code running, and I lowered it down to a single processor machine. And you can see that instead of scaling up like this little guy off into the distance, and then it looks like it would level out at about 200%. This one sticks clear. It gets up to the point where the overhead is not a big proportion of the total elapsed time, and then it just levels off. And then this is just another kind of got you experiment about how ThreadSleep doesn't actually indicate performance benchmarks.
Yeah, what did you mean?
So ThreadSleep tells the CPU, give up the rest of my time. The CPU gives each thread a unit of time to do whatever it wants with the process instructions. Or sorry, the OS, I guess. The OS gives the thread CPU time for a certain amount of time, and then it pulls it back and says, go back in the pool, and then gives another one CPU time. That's 15.625 milliseconds on a default Windows installation. It's probably not too far off for Linux systems and other things like that. But when you call ThreadSleep, you tell the OS, no matter how much you've used, 7 milliseconds, 2 milliseconds, doesn't matter. You tell the OS, I'm done, and it pulls it off immediately and puts it on the next one. So if you call ThreadSleep, what you're actually doing is talking about real duration time and not CPU time. So that's where it takes the performance optimization argument out of it. And so separate, I realize that should probably have a comma somewhere. So separate your refactoring efforts. Don't do a lot of refactoring and deal with concurrency at the same time. Do those separately. Redesign your system so that it supports concurrency, and then put concurrent operations into it. Design it for concurrency, but don't necessarily make use of concurrency. Then when you split things off into the different threads, then you know exactly how much performance you're going to get out of it. And it's not free, as you saw in those graphs. It actually took quite a while and a number of cycles before you were actually making use of the power that you have. I'll just finish off with a silly quote. But that is what I have. I have a couple more examples of some silly things that I haven't completely finished because I couldn't get them thread safe, funny enough. But that's about the end of the presentation. So thank you for coming, and we can have any questions at this point. I know I got just a bunch of questions during, so. But
You were asking if there was like a equivalent to OTP in like the .NET system. There's actually this one called Orleans. Not sure if you've heard of it.
which is it?
Orleans?
No.
ORLEANS.
Okay.
Yeah. Yeah, it's like Norman's, yeah.
And it
But
does
it's-
like a supervisor style
yeah,
of.
Yeah, as far as but I think it's experimental. But
Okay.
you can take a look at it.
Yeah. Neat.
Or you can just use Erlang.
Yeah, or just use Erlang. Yeah, Erlang's pretty cool actually. I've been learning it in my spare time, and it's a slick language. I should make note that Erlang in particular has been taking concurrency at a higher level respect. It's been treating it as a first-class citizen for decades, like, literally 30, 35 years, because it's been made use of like the European telecom system. So OTP stands for Open Telecom Platform. So that's like where it got its black belt basically. And then Go, the Google systems language, does the same thing. It treats concurrency at a higher level, so it on the same kind of idea as some of the new functional languages, or all the functional languages are treating functions as a first-class citizen and saying you can do anything with functions that you could with variables or objects or anything else. Now you can do that with concurrency as well. It's very respectful of it. So those two languages in particular have really cool approaches to concurrency.
Do you guys are looking into microservices, doing stuff with microservices? No? Have you heard the term? Yes? So microservices is a perfect example why a multi-platform solution could work, right? Because there's no reason why a service, if you're worried about concurrency, instead of trying to implement something in a language that is not made for that, right? The effort of learning something new will pay off.
Yeah, I found that like recently, languages aren't what matter, in my opinion. It's the frameworks. It's the power of the things that the massive groups of people have done to separate out the complexity and to wrap it in a framework is actually the more powerful thing than syntax or an individual programming's language ability to save you time. It's how these things are baked into the framework itself, and how does it actually run on systems that's important.
Unless it's early.
Especially if it's early.
So for those that aren't using microservices or having those conversations, I'm curious on so you mentioned the infrastructure component to this, where it's like, yeah, it's all bets are off when you're starting to do multi-threading and stuff like that, where you're going to just consume all of the resources of the server. I can just see that being great for the dev, and then like the infrastructure team is that group of people that just runs downstairs and is just like yelling at everybody. Mm-hmm. When do you include them on that conversation, and how do you even have that conversation with an infrastructure group? I'm just curious, outside of using Docker or containers.
So that's, like, in my personal experience, I don't like to see walls between the development and the operations department, nor do I like to see walls between development and QA. Mm-hmm. I think everybody should be involved in the problem from day one and not later on down the cycle. If you tell the operations department that you're going to require a quad-core processor to do a heck of a lot of math on one of your servers, but a single-core processor on the other one, like on the last day of the project, it's not going to go over well. So involve them from day one and work them into the conversation, because
keep them in the loop. They should be part of every meeting.
Yeah, if not sitting next to you, working out the problem with you. Like we're breaking down all the greater use of cloud is actually breaking down walls between developers and operations staff, and in many cases turning them into the same team, if not the same person. So, as early as possible.
So microprocessors, why are they good?
Microservices?
Microservices.
Yes.
Why are they good? How do they handle concurrency? Like, is it just one service on one core, or do they swap out? Like, what's up with that?
Yeah, so you can run, you can do whatever's right for the system. You have to find out what the load is going to consume if you're doing some really math heavy operations, and you can get into a system where some parallel operations on one of your service are going to end up starving another service. You'd want to separate that out to possibly another VM, so that it's on a more managed system and it's given an allotment of resources. Another strategy for dealing with that is taking that heavy math that's starving the other process and putting it into a pool and using like a maximum at a time kind of idea, so that you can only use up so much resources before. So it makes the process take longer because you're not using the whole thing into all of the available processing power, but you're also not starving the next guy over.
And also, besides that, the idea that when you need to scale, right? And when you need more speed, and you say, oh, how many more do I need? And being more of a monolithic app, right now, your solution, like Adam was saying, sometimes it's worth to just duplicate it, right? But sometimes duplicating is not what you want. So you say, okay, let's split this into tiny services with a very, very clear, small responsibility, and that will simplify what each of them do. But like Adam was saying with multithreading, you will pay the price that you have to coordinate them, right? And launch them, you need to spawn them, and then you need to say if they died, and who's doing what, with the reverse proxy, the load balancing. So it doesn't come free. It's a great idea, right? But it doesn't come free. So sometimes multithreading will provide that. Sometimes you go further and split in microservices, right? To be able to like Adam says, you have more VMs, right? You can keep spawning things and stuff like that. Doesn't mean that you cannot multi-thread each service, but this opens our architecture to lots of things that before we were just on one app and it was WPF or MVC and we stay there. Now it's completely open, right? Because maybe you still use WPF, but who's telling you that you cannot do the grunt of the work somewhere else, where it's faster, where it's cheaper, or it's whatever reason we may have. So that's the idea behind it.
I'm still not exactly sure how to code the solution to my problem.
Oh, come on.
Okay.
Bob, failed
Okay.
too.
So, yeah, all right.
Come on
I
out.
kind
We need a sponsorship.
of think I might have touched partway through when I was doing some of the queue examples, but reiterate.
So the problem that I have is I'm running a playlist. It's going to play through the list.
Right.
At the end of the list, it's going to check to see if there's a new playlist that should be running. I want to have that getting of the new playlist download all of the content when it can, and eventually update the next playlist object.
Yeah.
And then when I get to the end of the playlist, it will check to see if there is a new playlist, and then sure, I'll start playing the new playlist.
Yeah. So I would use concurrent, like a concurrent thread-safe collection to act as an intermediary in between those two operations, so that one could potentially poll regularly, just sit in a loop and try and check for existence of an entity or a flag or whatever you want to call it in a concurrent collection, a thread-safe collection, where it's responsible for firing up the operation, but then it just sits there and polls and waits for the result. And that other guy, after it's finished coming back it says it's finished downloading all the content, it just says, here, I've finished all the content, someone else can pick that up, and then I'm going to go download the next one or something like that. And you've got this one polling for a flag there, and now that the content is finished, we can check the result on the task, and we're going to come back.
What are you using now for the queue? To queue all the stuff to play?
Basically, I just have a list of playlist items.
Yeah.
And then I created in the same class a list of playlist items called next playlist. And then essentially doing go to the server, get it, fill the new playlist, and then switch them when I come back from the playlist, or from the end of the playlist. That works as far as concurrently. It just sits, the front end does nothing while it's waiting for the content to all be downloaded.
Right.
And
Yeah.
what do you want the front end to be doing?
Playing the existing playlist over and over.
But you have a thread in background doing that?
I have just the front end playing.
So you need to split up in another thread, right? Leave the UI thread
Exactly.
to play whatever, and then on the background is a concurrent queue, right?
Good cancellation request. So you wait until you get that cancel, and you keep playing the one until it's ready with the new playlist.
That could work.
But you're suggesting two threads, one like a main thread, and the other one is just polling. And
Yeah, I'd say use a concurrent queue, and then have one thread populating that queue,
Yeah.
and the other one consuming from the other side of it, and then have your UI thread talk to the thread that's consuming things off of the queue via like a concurrent thread-safe intermediary. Because you can use like a bag and have this thread-safe bag sit in memory and have these two, your main thread and your other thread, check just to see if there's anything there, and sort of talk to each other through an intermediary.
Sure.
So question, assuming we were executing, we got to a point where we called a method that goes to load all the new playlist items, right? And then we had a loop that was just playing the current playlist items.
Mm-hmm.
We have to, so we are returning a task and we have to await on that task at some point, right?
Mhm.
So we are loading all of the playlist items. We have a loop, so it just, once the await is called in that task, it comes to the original method and continues execution.
Yeah.
Now we're looping through the existing playlist and we're playing all the items. At what point do we await for the task that has loaded all of the items? So at what point do we say, oh, it's done, let's now switch out to playlist for a new one?
Right. Well, you can periodically check if the task is completed. There's a flag on it, so you don't necessarily have to await it and block your thread to wait on the task.
Oh.
You can check if it's done.
How? What's the command?
It's is completed. It's a Boolean flag that sits on the task.
Yeah, I think that would help you, because if you have a loop and you have a list of items, you can just keep cycling through, playing all of that. And at the end, you can just check, oh, is this task completed? If yes, swap out the playlist for the new list that has been populated in the asynchronous method, and then just keep playing. Does that make sense?
Yeah.
Okay. I think
Come
that's
on,
Do you at least have more ideas to go back
I
to?
have more ideas
All right,
and more
good.
code to.
I'll
So Adam
settle
will
for
send
that.
you an invoice after the session here, and
Would
pizza's on you next time. Let's get it.
would reactive extensions help with this?
With which?
With an example like this, using the reactive extensions. So you don't need to wait, and you can treat it as a stream.
Oh. I'm not sure.
You populate it in from one side and straight it out the other, right?
Yeah, because it looks like that, right? Like an infinite stream of things. And I think the reactive extensions could be a good fit for that. Or at least nobody's saying no. So.
I think I think the queue might work. I'll only ever have one thing in the queue. It'll be nothing or something.
Right.
So if there is
Can
something
you
in the
have
queue,
two playlists?
Well, that's still a reasonable way to
yeah,
you
Can-
just
can
single
you
item
have two
stack
playlists in
or
the
whatever.
queue?
sure, but the current playlist isn't in the queue. It's being used.
No, well, but can you have one more after that?
In this scenario, I would.
No. Okay.
That could theoretically work if you had like a system that had 100 playlists that were coming in at random
Yeah.
intervals. Sure. In this instance, it's more of a every so often check and see if someone's uploaded a new playlist, and then I'll start playing the new playlist once I
Right.
have all that content.
Well, you can
Correct.
say that you prepared for more and ask for a raise.
Look at that, you asked a question.
Now it works
how
for
you-
N.
You've added features to your project, so.
I got a raise.
Yes, exactly. Raise and scope creep, it's fantastic.
That's another interesting point. Never design for two. Design for one or N. And like I think that really applies with concurrency as well.
Cool.
You had at the end of your section on divergence, you had the continue with scenario with the tasks. When would you use that situation versus just having, await this, await this, await this, and sequence kind of thing?
You can set up the task that goes to continue with, and then get on with the rest of your life. You don't have to sit in that method and await this and then schedule the next one and await this and then schedule the next one. You can set up the entire process chain at the beginning, let it go, and then go do something else. So you're just queuing up more work, and you're being more explicit about what chains into the next thing, and not allowing it allows for less visual complexity, that you can see that one task is specifically being followed by another one as well. As far as like the difference in actual operations, it's not, but the difference in syntax and organization is worth it.
It's more
In my opinion.
than actual.
Yeah, I would say it's more of an organizational thing. Yeah.
Isn't this similar to like JavaScript promises? And
Yeah, that's,
Yeah, the task is a little like a promise, except that except for the whole await thing, that you have to get to an
Yeah.
await before you're actually diverging. Whereas promises are like diverging immediately, and then you go off with whatever
I
you're
saw
doing.
Douglas Crawford talking about or your framework he wrote that do the same thing, wait for all, right?
Mhm.
All that stuff, it's common to see in other languages as well. The same idea. Are we good?
I think so.
Okay.
Cool.
All right, thanks a lot, everyone.
Awesome.
Thanks.